Alrighty, everybody, it is 11 a.m. So we are going to go ahead and get started. Welcome to our 13th lecture of OCSP. It's week 5, so you guys are more than halfway done already. And let's go ahead and get started. So today we're going to talk about how to figure out when each of the 4 big reactions, SN1, SN2, E1, E2, is going to take place. And we're also going to talk a little bit about a concept known as Bredts Rule. So before we get into some new information, I wanted to just reiterate that reactions often come in pairs. So whenever you see an SN1 reaction, frequently you're going to see an E1 reaction along with it. And same goes for SN2. Frequently with SN2 reactions, you'll see an E2 reaction. So just keep those in mind. So this is an example of a problem that you could expect to see in a 3570 homework assignment or especially on the exam. Sometimes they'll ask you to just predict the product, and sometimes they might ask you for the mechanism. So it's important to be able to know how to analyze all the factors given to you so that you can come up with the best possible answer. So right here on the screen, I see that we have 3 different molecules. We have this starting material, we've got our arrow with this molecule above and this molecule below. Does anyone want to unmute themselves or type in the chat and talk about what type of molecule any of these 3 are? Well, I see right here that we have NaSH, which, as we discussed about a little bit last week, this is a nucleophile. So one factor that when we're trying to figure out, is this going to be an SN1 reaction, an E1 reaction, E2, what type of reaction is taking place here, we can look at our attacking molecule and see, is it a nucleophile, a base, how strong is it, that sort of thing. So this is actually a pretty decent nucleophile. Now, we have our solvent down below. Does anyone remember from Friday what type of solvent DMSO is?
Polar aprotic.
Thank you, Anzilla. So DMSO is the solvent, and it happens to be polar aprotic. And if we know that the solvent is polar aprotic, that gives us some clues about which reactions are going to be the most favorable. Also, just housekeeping, frequently the nucleophile or attacking molecule is going to be on top of the arrow, and oftentimes the solvent is below the arrow. Just that happens a lot of the time. So if you're struggling to figure out which is which, try looking for the solvent under the arrow. Then we can look for more clues at our starting molecule, which is over here. So on the starting molecule, there are 2 different clues that we can try to find. We can look at our leaving group, which here is OTS. And we can consider, is this leaving group going to be stable after it leaves the substrate? You know, is it something that might need to get kicked off, or is it something that's going to be able to leave on its own? And then lastly, well, first of all, can anybody guess what the second clue we could find on our substrate is?
What kind of cation forms once the group leaves?
I'm sorry, could you repeat that?
What kind of cation forms once the group leaves?
Exactly. Thank you, Kunal. So we can look at our substrate, and just like Cornell said, we can think about what type of carbocation would form if the leaving group leaves. Is there a lot of steric hindrance on our substrate? You know, could a backside attack occur easily, or would this molecule be stable as a carbocation? So I'll write substrate down here. So all of these clues are sort of things we can look at like a detective if we see a problem like this and we're trying to figure out what type of reaction and thus what type of products are going to form. So one factor that we can look at first is the alkyl substrate. And a lot of these points are probably going to be reviewed, but we just wanted to go over them clearly as we're going to get more into sort of synthesis and problem solving with the 4 reactions this week. So if you see a primary substrate, your reaction must be an SN2 or E2 reaction. And here's just an example of a primary substrate. Does anybody remember why a primary substrate must be an SN2 or E2 reaction?
So it becomes easier to do a backside attack.
Yep, you're right about that. We can have a backside attack occur really easily on a primary substrate for an SN2. Great, thank you. On a primary substrate, it also isn't going to be super stable for a carbocation intermediate to form. So those are both reasons why primary substrates indicate SN2 or E2. Alrighty. Next, if you see a tertiary substrate, your reaction must be SN1, E1, or E2. Can anybody remember why SN2 reactions do not occur with tertiary substrates?
If you want a backhand or backside attack, that would just be too heavy, and so it wouldn't occur. So you would need something lighter. So that's why it has to be SN1, E1.
Exactly. Thank you so much. So just like Cornell said, a backside attack would be really difficult to do on a molecule with so much steric hindrance. And this molecule, for our 1-type reactions, it would be pretty stable as a carbocation intermediate. So that's another factor that would make SN1 or E1 reactions more likely. Also, E2 reactions have a lot less steric concerns than SN2. So that's just something else to keep in mind. And then lastly, if you have a secondary substrate, you can't rule anything out because all 4 reactions are possible. So when you see secondary substrates, it's best to just recognize that and try to look at the other factors for more clues. Any questions about substrates before we move on? Alrighty.
Wait, I have a question.
Go ahead.
Why does E2 have less steric concerns than SN2?
Good question. So both of those reactions are concerted, but only the SN2 reaction has a backside attack. If you remember from last week in the E2 reaction, you just need to have a base take that anti-periplanar hydrogen in the E2 reaction. But if you have a molecule, it can still do that on a molecule that has more steric hindrance. Did that kind of answer your question?
Yeah, it did. Thanks.
Okay. Anything else? Alrighty. So a second factor that we can look at when we're trying to figure out what type of reactions can take place is a solvent. And I know that Corel and Brendan kind of talked about this on Friday, but it's definitely good to review. Polar protic solvents tend to favor SN1 and E1 reactions. Can anybody give me an example of a polar protic solvent? Well, some pretty good examples include H2O and methanol. So those are some examples. And does anyone remember why you might have SN1 and E1 reactions being stabilized in polar protic solvents?
Because of the negative charge could dissipate like throughout the solvents.
Okay, thank you, Alex. I like it. Because, like you were talking about, there is both cation and anion, I believe, solvation in polar protic solvents. That's going to be really stabilizing for our intermediates. So there's that. And then we have polar aprotic solvents like DMSO, that's a popular one, or HMPA, that's another one you might see that's polar aprotic. Those tend to favor SN2 reactions. And does anyone remember why polar aprotic solvents might favor an SN2 reaction? Well, both polar protic and polar aprotic solvents have anion solvation, but polar aprotics are just kind of mediocre at it. And that can be sort of stabilizing for the nucleophile in an SN2 reaction. And in addition, DMSO doesn't do hydrogen bonding, so it allows a nucleophile to move really quickly to do the backside attack. And then, lastly, your E2 reaction can occur in either a polar aprotic or a polar protic solvents. While you won't see SN2 reactions really occurring in polar protic solvents, E2 reactions can occur in both. So that's just something to keep in mind. Any questions about solvents before we move on? Also, I just wanted to correct myself. I can't remember if I said polar aprotic have anion or cation, but polar aprotic solvents do not have anion solvation. They only do cation solvation. Sorry if I said that incorrectly. So I'll write plus and minus solvation up here, just to make things clear. And I'll write plus solvation only for polar aprotic. Any questions? Alrighty. So let's go ahead and look at another factor when we're trying to figure out what reaction is going to take place. And we can look at the attacking molecule. Now, I use the term attacking molecule because with our four reactions, we can be looking at an attacking molecule that is a nucleophile or a base, or both. So here we have four examples of different attacking molecules. And if you're in my study group, you've probably already seen a version of this slide. We have molecules that are only nucleophiles. Those include your sulfur nucleophiles like SH- and H2S, as well as any halides such as Cl-, Br-, and I-. These molecules are generally considered to be too weak to act as bases. And so they're going to do usually only the substitution reactions and not elimination reactions. And if you're trying to decide whether these nucleophiles will do SN1 or SN2 reactions, try looking at the substrate to see if there's going to be steric hindrance or a stable carbocation. In our second category of attacking molecules, we have molecules which are both really strong nucleophiles and really strong bases. Now, these molecules include familiar looking OH- and minus OCH3. So these molecules are going to be able to do SN2 and E2 reactions. They're going to be strong enough to attack through the backside attack for an SN2 reaction, or really grab the anti-periplanar hydrogen in an E2 reaction. Now keep in mind, this is assuming that all the stereochemistry and steric constraints are met. Now, you might be wondering why I said usually SN1, SN2, or E2, and I didn't put SN1 or E1 here. And that's because generally, if the steric constraints are met, a faster reaction without an intermediate is going to dominate over a slower one-type reaction that does have an intermediate. So that's why the stronger bases and the stronger nucleophiles, or the molecules that are both, normally do those concerted reactions. Our third category of molecules is molecules that are only strong bases. So here we have tert butoxide, which I think I gave this molecule as an example last week when I talked about nucleophiles that have too much steric hindrance. So this is what tert butoxide looks like. If you haven't seen it, it's important to be able to recognize it from both the molecule and from its formula, which is right here. And it's a fantastic base. It's very often seen in E2 reactions. In fact, I think it's mostly seen in E2 reactions. And it's what you might hear referred to as a big, bulky base. That just means it has a lot of steric hindrance, which is why this molecule does not usually act as a nucleophile because it can't move fast. However, it's still wonderful at grabbing that anti-periplanar hydrogen for the E2 reaction. And then, of course, we have NaH, where Na plus is the spectator ion, and we have H minus, which is too small to act as a nucleophile, but can be used to deprotonate stuff. So these types of strong bases are usually only seen in E2 reactions, assuming the substrate has all the stereochemical constraints met. And then lastly, we have molecules which are both weak nucleophiles and weak bases. And these two examples might look familiar, H2O and methanol. You might recognize them as they're both polar protic solvents. If you remember from Friday, we talked about solvolysis reactions, where you might have a polar protic solvent that actually acts as either the nucleophile or the base in a reaction. And these group of attacking molecules, the ones that are weak nucleophiles and weak bases, those usually do just SN1 and E1 because they're not strong enough to do any sort of concerted reaction. So, are there any questions about attacking molecules or anything that I've talked about on this slide that I can answer? Alrighty. So now we're going to go ahead and talk a little bit about solvent effects on nucleophiles, since we did introduce solvents on Friday. So oftentimes in 3570, you'll be given problems where they give you a couple of nucleophiles and they'll say, okay, there's X solvent, which nucleophile is the best? Or rank these nucleophiles from least to worst. So these problems and understanding the effects on solvents are often pretty high yield. So if you're comparing two nucleophiles and they're the same size, any sort of solvent is going to have the same effect. And what I mean by that is, let's say we have a solvent that's H2O, and we have OCH3 minus and minus SCH3 minus. Obviously, the negative charge would be on a different atom, but that would be an example of nucleophiles which are the same size. So the solvent would have equal effect on nucleophiles with roughly the same amount of size. So now we're going to talk about two situations where the nucleophiles might be different sizes. So in polar aprotic solvents, smaller nucleophiles are better. Generally, nucleophilicity in polar aprotic solvents parallels basicity. And usually the trend goes that smaller atoms are better bases. Thus, in polar aprotic solvents, smaller nucleophiles are also going to be preferred. Remember that in polar aprotic solvents, there's no anion solvation or H bonding, and it's easier for a smaller nucleophile to move faster in polar aprotic solvents because there's not going to be anything that's really inhibiting the nucleophile from moving, like solvation or hydrogen bonding. So these factors all kind of go back to the whole SN2 reactions are really, really preferent in polar aprotic solvents. Next, we have polar protic solvents, and we can compare sizes of nucleophiles there as well. So remember, polar protic solvents have both anion and cation solvation, as well as hydrogen bonding. So larger molecules are not going to be bogged down by that solvation as easily. So for example, suppose I have I-, which is a pretty big halogen, and I'm going to draw my water molecules around here. And this isn't hydrogen bonding. This is just like an example of like solvation. The I- is pretty big, so it's still going to be able to move through the polar protic solvent. In comparison, if I had a really small nucleophile, it would not be able to do that as easily. There's also hydrogen bonding going on, so that's just another factor that makes a larger nucleophile better in polar protic solvents. Are there any questions about solvents and their effects on nucleophiles that we can answer? So to reinforce what we just learned, we have a quick practice problem for you guys. This is an example of something that you could expect to see on an exam or on a homework assignment for 3570 or for our course this week. Which nucleophile out of the 4 below would react the fastest in DMSO? So I guess a supplementary question that we could ask is, what type of solvent is DMSO? Does anybody remember?
Polar aprotic.
Thank you. Thank you, thank you. Just as Krinal said, DMSO is a polar aprotic solvent.
Would it be I minus?
So in polar aprotic solvents, do you remember if it's the larger nucleophiles that are best or the smaller nucleophiles that are best?
Smaller?
Yes, exactly. So it's interesting because the trend kind of flips, especially when we're comparing different halogens, because that's a great example of nucleophiles that are all different sizes. In polar aprotic, you want the smallest possible nucleophile because it can move the fastest, and it doesn't have any solvation to worry about. In polar protic solvents, because there is anion and cation solvation, you want the biggest nucleophile so it can kind of push through all that and push through the hydrogen bonding that goes on in the solvent. So we're looking at a polar aprotic solvent here. So we're going to want to pick the smallest nucleophile as the most nucleophilic and the fastest reacting. So which of the 4 examples here is the smallest?
F minus.
Absolutely, thank you, Nestor. So we've got F minus as our very best nucleophile in this polar aprotic solution. Then we've got our Cl minus because it's the next smallest. And then our Br minus, and lastly, our I minus. And it's of course important to note that if we threw these 4 nucleophiles into a polar protic solvent, the trend would instantly reverse. And I'll go ahead and write that there. So in polar protic, I minus would be the first. And then we would have Br minus. And then we would have Cl minus. And F minus would be the absolute worst. Any questions about these trends? Alrighty. So another factor to look at when you're trying to pick clues about which reaction is going to occur in solution, or when you see a problem and you're trying to decide what the product is, remember that temperature can also be a factor. So if you see this little heat sign, that means that heat favors an E1 reaction. And this factor is often the most useful if you've got one of those substrates and you have a molecule that's a weak nucleophile and a weak base. So if you have maybe something like this, I'll add a Br right here, and you have maybe some methanol. This molecule is going to act as both a polar protic solvent and a weak nucleophile base. And this is important because our solvent is actually acting as the weak nucleophile cis base. So our outcome for this reaction could be SN1 or E1, because the molecule is a weak nucleophile and base. But if I were to throw in the heat symbol right here, E1 would definitely predominate, or dominate rather. So this is definitely a big clue. Any questions about this? All right. I will go ahead and pass it over to Samantha.
Thank you. I drank a lot of caffeine this morning, so I'm a little bit crazy, but please forgive me. Let me see if this will share. Come on. No, it doesn't want to. Give me 1 second. There it is. Can everyone see this? Let me get rid of the faces real quick. There we go. Okay, so we're actually going to go back to our original example, and we're going to see again that we have this OTS molecule with NaSH and DMSO, and like Sydney said, DMSO is going to be a polar aprotic solvent. This NaSH is going to be a good nucleophile, but not a very good base. So not a strong base. And so the reason why this is a good nucleophile, remember, is going to be because of that sulfur. You can imagine like having the SH minus and then maybe the Na plus. And so based on these two things, do you guys have any idea what kind of reaction this might be?
SN2?
Yes, exactly. I don't know who said that, but good job. So this is going to be an SN2. And so because these reactions sometimes come in pairs, we want to think about E2. The reason why E2 is actually not going to work is because, remember, this is not a strong base. E2 usually wants a strong base so then it can take off that anti-periplanar hydrogen and deprotonate the whole molecule. In this case, we do not have that. And so we're going to go ahead and do an SN2 reaction, and we should get the following. Remember, you're going to invert your stereochemistry, so you go from having a wedge to having dash. Something else I forgot to mention is that the substrate is secondary. In this case, it's not that important to know because remember, only primary and tertiary really help you kind of like parse out what kind of reaction this might be. For secondary, you can pretty much have anything. Does anyone have any questions on that? All right, so we're going to be doing some more practice. So here's our next molecule in reaction. We're going to have CH3OH, and that is going to be what kind of solvent? Does anyone know?
Polar aprotic.
Yeah, exactly. It's going to be polar aprotic. Also, not particularly a good nucleophile or base. And so we also want to look at our substrate. If we look at him, we're going to see he's tertiary. Remember, here's the carbon, 1, 2, 3. And so based on these things, based on tertiary, we can say, okay, well, it's probably either SN1, E1, or E2, which is a lot of reactions, not super helpful. But again, we can look at the solvent and go, okay, he's not a good base, get rid of the E2. And so based on this, we're actually going to have two reactions. So we're going to have the SN1 pathway. I'll draw that bigger. And we're also going to have the E1 pathway. So this would be an example of a reaction where you actually have these two pathways, these two guys coming in pairs. And if you remember, like Sydney just said, E1 will be favored if there's heat. So if, for example, I put heat here, then you would favor the E1.
Sam,
Sorry, say that again?
sorry to interrupt. CH3OH is polar protic.
Oh my God, sorry. Did I say polar aprotic? Ignore me.
Didn't want to interrupt. Sorry about that.
No, yeah, thank you. My brain had a fart. Yes, this is polar protic. Sorry if I confused anyone. Remember, this hydrogen is going to be right here. Does that make sense to everyone? This is why you don't drink too much coffee, guys. So now, let me check the other one. Yeah, he's okay. So now we're gonna do this last practice. Again, we wanna look at our substrate. Secondary, not super helpful. I'm gonna draw on this hydrogen, just so you guys remember. Remember, he's just gonna be a CH3 up here. And so NaOH is gonna be both a strong base and a strong nucleophile. And so immediately we're gonna think, okay, maybe SN2, maybe also E2. And so we wanna think about those two. So first, we can go ahead and draw our SN2. Remember to invert your stereochemistry. This is one of the ones where it's kind of gross to draw like a wedge instead of a dash, so I'm just gonna go ahead and flip it. If you have any questions on this, again, let me know. Let's see. OH, these two guys. And so now we want to think about E2. And so E2, again, is actually not going to happen, but for slightly different reason. So remember, when you're doing your E2, you're going to want to take off an anti-hydrogen, or rather a hydrogen that's anti to whatever your leaving group is. And we're going to actually see here that if Cl is the leaving group, this is a wedge, this hydrogen is also in a wedge. So these are not anti, these are syn. That's why E2 cannot work. We can always check the carbon that is on the other side of the Cl, and we're going to see that there are no hydrogens to take off, just these methyl groups. So we're going to leave him alone. So I will go ahead and draw what you would have if it were E2, but I'm going to cross it out. So theoretically, I believe it should be something like this, but again, we're going to cross that out because the hydrogen is not anti. Anyone have questions on that? Okay, so now we're going to be talking a little bit about ring compounds. This should be review, I believe, but if it's not, don't worry about it because it's not that big of a deal. And so if you remember, spirocyclic compounds are going to be when you have a ring compound with two rings and they share one atom. So for example, you have this guy, spiral 4,4 nonane. So you're going to see right here, that's where they share a carbon. And so you also have bicyclic compounds. Those usually have like bicycle or something at the beginning. And that's when you have two rings sharing two or more atoms. You have these two general types that are called fused, where I believe it's only two carbons. Let me think. That sounds right. Usually you're going to see only two carbons in a fused, and you're going to see that they're kind of all in the same plane. They don't stick up. Whereas in something like a bridged bicyclo compound, you're going to see this thing sticking up. This, I believe, is called just the bridge. We will get more into that in a second. And you're going to see that this guy is not in the same plane as the rest of the ring. And then your last one is going to be your polycyclic compounds. Those are usually more than two rings. They have a bunch of common atoms generally. So you got these guys like cubane, which I think are fun, where they're like, a lot of them are connected. You get like really fun looking 3D shapes with that. And so now we're going to keep going. So this is sort of an important concept, bridgehead atoms. So generally these are going to be carbons, but basically in any kind of polycyclic molecule is an atom that is part of 2 or more rings. Generally it's going to be a carbon. Once in a while, I believe you can have like a nitrogen or something. So in a fused ring, remember this is fused, this is bridge. You're going to see that these two would be the bridgehead atoms because they are connected to the rest of the rings. And this next one, in this bicyclic compound, 1 and 4 are going to be the bridgehead atoms. You can see that they're connected to, if you imagine, I'll show you another picture, but if you imagine these 2 rings as 2 separate rings, they're going to be connected to both. Generally, this guy at the top is not considered a bridgehead. And then lastly, if you remember cubane, these are all bridgehead atoms. You don't really need to know this. I just thought this looked fun and kind of crazy, so I put it in there. But generally, when we talk about bridgehead atoms, we will be talking about these bicyclo-bridged compounds. And so also want to bring your attention to something real quick before we get to Bredts Rule, and that is going to be that you can draw these bridge bicycle compounds a bunch of different ways. I know when I was first taking Orgo, it was kind of confusing because then I had to like think about this and think about how that was the same to this. And when you have a model kit, this will make more sense. But just know that you can draw it. You can draw these bridged bicycle compounds in kind of a flat structure, or you can draw them in the sort of chair conformation. And you want to remember that the bridgehead atoms, where they come up to meet, they're always going to be syn. So in this case, they're both wedges. They can be both dashes. Sometimes you'll see them just drawn as lines, like if they don't really care that much about stereochemistry. And that's just going to be because you can imagine, like in this 3D molecule, they're all pointing to the same place. They can either be pointing up or be pointing down. It doesn't really make sense for one line to point up and one line to point down because then they don't meet. And I can also go ahead and label these. And you'll see that this is the same compound as that, which is the same as this. Does that make sense to everyone? So finally, we'll be talking about Bredts Rule. And remember that when we talk about it, we're generally going to be talking about bridged bicyclic rings. My iPad doesn't want to be nice. So these kinds of guys at the bottom. And so for a ring system with less than 8 carbons, you can't have a double bond on a bridgehead atom. And so why doesn't this work? It's easier to see with the model kit, which unfortunately I don't have at the moment. But basically, if you tried to build that model kit, I believe you'll have some ring strain, and you will also have to twist the double bond, which will just like break your structure. But the actual chemistry reason is because when you have those 2 double bonded carbons, their adjacent p orbitals don't overlap very well. And remember, you're going to need that in order to have that pi bond that double bonds need. So unfortunately, that does not work super well. There are like a few exceptions, I believe, to this rule, and I think they're called anti-Bredt molecules, but we didn't even learn about that, so you don't have to worry about that. There are some like really cool papers out on them though, so if you're interested. They're generally like really giant molecules, so they're kind of whack looking. So if we look at these 3 guys at the bottom, we can see which ones are following the rule or not. So I'm just going to label these 1, 2, and 3. And I'm going to go ahead and label the bridgehead atoms. Remember, it's going to be 1 and 4 in this case. And so based on these pictures, there's only one molecule that follows Bredts Rule. Do you guys know what it is?
The first one?
Yeah, exactly. The first one's going to follow it because if you see, there's a double bond here, but it is not connected to any of the bridgehead atoms. So he's okay. He's not okay. He's not okay. Because you're going to see, in this case, I think they're actually, yeah, they're both connected to 1. You could have just drawn a double bond connected to 4, and that would also break the rule. So yeah. So now we're going to be doing a little bit of practice. So we want to see which of the following molecules follows Bredts Rule. And so we already talked about this guy. He's all good. Because remember, bridgehead atoms are going to be 1, 4. On the middle guy, they're going to be these two. Last guy, they're going to be these two. And so this guy in the middle, do you think he follows Bredts Rule or not? Remember, that's for rings of less than 8 carbons. So he is not going to follow Bredts Rule, because if we go ahead and count around the ring, or sorry, he is going to follow Bredts Rule. My brain is lit today. It doesn't really apply to him because he has more than 8 carbons. He's okay. This double bond is all right. Sorry, that was confusing. Anyone have any questions on this middle guy? Sorry, I misspoke. Now we're on this last guy. So we can go ahead and count around again. 1, 2, 3, 4, 5, 6, 7. Remember, the ring is just going to be this bottom part. And we're going to see he's only 7, so this is not good. He is not more than 8. He is breaking Bredts Rule. Anyone have any questions on that? All right, so we're going to be going on to our last practice. We're almost there. And so we're going to say, which of the following could have double bonds of bridgehead atoms? So all we need to do again is think about, okay, what's Bredts Rule asking? It's no double bonds if you have less than 8 carbons. Did I write less than 8 or more than? Yeah, we're good. And so remember, this does not apply to fused rings. So this guy is actually okay. He could have a double bond here, for example. He is all good. He is not bridged. Let's look at this guy on the left and top. I can go ahead and count these out for you if you want, but I think you'll see that this is definitely going to have at least 8 carbons. So yeah, he could have a double bond there or something. He's all good. Go to his friend at the bottom. You can see this is only 6 in this ring, and then the 7th up here. That one doesn't really matter. So again, you could not have a double bond here. That'd be bad. And then this last guy, I think you will also see that he definitely has at least 8. So he is all good to have double bond on a bridgehead atom. Does that make sense to everyone? And that's actually going to be the end of our lecture. If you want me to go back to any slides, because I think I went a little bit fast, please let me know. Then other than that, I'll just be here for questions, that kind of thing. Or if anyone has any questions in general, Sydney and I can talk about them.
Can you please go back to the slide that said quick review of ring compounds?
What slide was it? Could you say that again?
I think it says quick review of ring compounds.
Quick review of ring compounds, gotcha. Was it this one or the second?
Yeah, this one. Thank you.
All right, polycyclic next to this guy. And also, this is not so important, but I believe that these definitions aren't always mutually exclusive. You can call, I've seen people call spirocyclic and bicyclic compounds polycyclic before, just because of course they're more than one ring, but that is not that important. I'm gonna be right back. Sydney should be here for the next couple minutes at least. If you guys have any questions though.
Yeah, I would be happy to help if anything wasn't clear.
Could you go over why E2 reactions occur in both polar aprotic and polar protic solvents?
Sure, I'd be happy to. Let me see. Oh, it looks like Samantha's still screen sharing. I wonder if I can override that. Alrighty, let me see which slide it might have been on. It might not have had its own slide. Basically, the idea of why like E2 reactions can occur in polar aprotic or polar protic, I think there's several reasons. First of all, an SN2 reaction, which is limited by polar protic solvents, SN2 needs a nucleophile that can move really fast, that's super strong, that can do that backside attack. E2 reactions do not have a nucleophile per se. They just have a base that takes the hydrogen. It definitely that reaction looks like it has a lot less steric constraints than SN2. In addition, we talked a little bit about the bulky bases that are frequently used in E2 reactions, such as, trying to find it. Oh, there it goes. The tert butoxide. So just as I think a large nucleophile can push through a polar protic solvent, a big bulky base that's often used in E2 reactions will also likely be able to push through and still be able to do a concerted reaction. While for SN2, like you wouldn't be able to have a nucleophile with this much steric hindrance kind of going on. So because of the different factors that are impacting the E2 reaction, I think that's why it can still occur in both polar protic and polar aprotic solutions. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, my pleasure. Well, I actually have to run to teach another class, but if you guys have any questions, you are of course welcome to come to office hours. I believe there's some today. Sign up for tutoring, and good luck with everything.